Look at a few things, right? As an object moves in a straight line, we need to remember what is distance, displacement, speed, velocity, and later on we look at something called acceleration, right? So let's take a look at these things here. So imagine you have a car, right? And the car is traveling from point A to point B. When the car reaches at point B, the car would have covered a total distance. So the total length traveled by the object is called the distance traveled. SI unit, meters, and it's also a scalar quantity. What's a scalar quantity again? A scalar quantity has magnitude only, right? So a scalar quantity has magnitude only, while a vector quantity has magnitude and direction. Okay, so distance is just a scalar quantity. So the total length traveled is a distance. On the other hand, displacement is the distance traveled from a stated direction or distance from a starting point. So for example, if I ask you for the displacement covered here, that will simply be the straight line distance from A to B. But let's say the person went down to C now. Let's say the car went to C. Right? The total distance traveled will be A to B to C. Add up all of that. But the total displacement will be the distance from where you start to where you finish. So that's AC. Remember that? Right? So your displacement is the straight line distance from start to finish. Right? I can make a note of that. Displacement is your straight line distance from start to finish. Straight line distance from start to finish. Straight line distance from start to finish, right? So please note that is a vector quantity, SI unit meters. As I said, everything in your handout, right? But I just wanted to get an idea of what's going on. I will never write this again, no? Let this up. Let this up. This is a replica, right? I'm gonna see that figure that up. Why don't you just spell it wrong or something? Right, so as I said, this distance here, right, is the distance traveled. If we go down to C, this is your displacement here, right? Distance from where you start to where you finish, right? Right, next we want to take a look at speed. So if I said, okay, what's the speed that the car was moving with, right, while traveling from A to B? What you have to find is the distance traveled and then divided by the time taken. Distance divided by time is speed. SI unit, meters over seconds, so that's meters per second. Okay, that's the speed travel. Notice speed is a scalar quantity. Okay, so if I ask you to find speed, direction don't matter, just find distance divided with time. Okay. Now, what is velocity? Very similar, right? If an object is moving, it has velocity, but it's a little bit different because velocity is the displacement per unit time. SI unit, meters per second. Okay? So this, on the other hand, is not a scalar quantity, it's a vector quantity. Right? So direction matters here. Direction is important. So for example, if something moving to the right, we might consider the velocity here as being positive. If something moves to the left, direction change, so the velocity is negative. Okay? So direction is important, right? So I want you to make a note of that. Direction is important because it's a vector quantity. All right, so nice. So let's see if we can try a real life example. Let's see if we can try a real life example of this, right? So let's say we have a car. We have a car and the car is traveling. Let's say the car is traveling. Let's try one like this first. The car is traveling at 50 meters per second. Let me say 6. And there's a little sign here. Speed limit. And the speed limit is 100 kilometers per hour. Right, the speed limit here is 100 kilometers per hour. So car moving that way, you have a thing there, you have a little police on this side. Is the car over the speed limit? Is it? So here we have Adrian. We have the speed limit at 100 kilometers per hour. Right? We have the speed limit at 100 kilometers per hour. And we have a car. That car is moving with a speed of 60 meters per second. Question is, will the car, is the car going over the speed limit? What's the first thing that we need to do? Calculate them, right? We need to make sure that they are both in the same SI unit. Here we have meters per second, here we have kilometers per hour. Right? So we have to convert them to the same thing. So let's try to convert kilometers per hour to meters per second. Right? What's the first step? The first step is I have to convert the kilometers to meters. How you do that? Multiply by 1,000. Next step, I have to convert the hours to seconds. How you do that? So what you do is you want to take the hour. Remember, this is 1 hour. I want to get in 1 second. So what you just do is divide by 3600. Okay? But so for example, if I give you 100 kilometers per hour to meters per second, right? All we have to do is take 100, multiply it by 1,000, and then divide it by 3,600. How much you get there? That'll be your answer in meters per second. How much is that? And you can cancel up and then divide 1,000. 36 in that 1,000. So, 27.7 meters per second. So what does that mean? This should really be reading 27.7 meters per second. So what will happen? Right over the limit. Over the limit. You okay with that? It will always work in the same SI unit, right? So to convert kilometers per hour to meters per second, multiply and divide. See if you can figure out the other way around now. See if you can figure out the other way around. Try that faster. right? So what do? Number one, we divide by 1,000, and number two, we multiply by 3,600. So I'll take it as an example. I'll take 60 meters per second and convert it to kilometers per hour. So so divide by 1,000 and then multiply by 3,600. How much you all got? How much? 216? 216 kilometers per hour. So you can definitely see how much faster this is. Yeah. What do you call a number that sit still? That's not what this one is doing. See it something. Yeah, I'm gonna use that next. I'm using that tomorrow. Have a next one when I'm post up the next one. That's right. Are you okay with that? So it must be in the same SI unit, right? Right. Well, there's a short way. There's a next way that you can next way you can if you want to memorize it, right? I don't really like the memorizing thing, but do me a favor. Take 1,000 and divide it by 3,600. Tell me how much you get. 0.27. So if you multiply your kilometers per hour by 0.27, you will get your value in meters per second. And here, this one is 0. No, sorry, this one is 3.6. Yeah, I use that already. I use that one already. I use that in the beginning. That's my first video. That's the one I went to wait. I think I didn't use that. I didn't use that. 3.6. I use something with food though. But the one with tables are like I use that yesterday. Are you okay with that? Right. So if you don't remember this, that's okay. Right? If you don't remember this, you should remember this, right? All right. So that's speed, velocity. We have one more thing to look at called acceleration. Right? And that's acceleration. Right? I just want to show you something after. Right? So what is simulation here? Let's see if this movement matter what today. What's it working before? Let me see if it's working. Online, you're seeing a share screen, right? It might be blank. right? It might be a little dark. Online, you'll see the share screen. Our man there. Sarah, take the screen. All right. So we have a guy here. He's at position 0, and we're going to move him, right? Let's increase his velocity a little bit. Right, if his velocity is about 0.6 meters per second, right? What you will notice, how do I make this flat? Right, you'll see how long it take it to reach point A or B, right? That's not what they're trying to show you acceleration here, but how to. We'll make this thing larger. And basically how to make this screen larger. I'm not going to see acceleration.
There's a science thing.
What sign is that? All right, I'm trying to get acceleration to show you something, but all right. Anyway, before that, right? If I were to keep his velocity positive, you'll recognize Frankie when he's staying on the right side. But if I change his velocity now to be negative, then he starts to go in the opposite direction. Are you okay with that? Right, but I wanted to show you something with acceleration. I don't know how to get down there. All right. So, all right, let's try the next simulation, right? Maybe it might be. Right. So as the girl chose down the apple, right? I want to take a look at the graph. Look at the distance time graph and look at the velocity time graph. Look how it's behaving, right? So as it falling, distance getting bigger, velocity changing. But you see the velocity is a nice straight line. So the velocity constantly increasing. All right. So as the velocity changes with time, what we're really observing there is the acceleration of the apple. Right? You guys ever heard about gravity? G? Right? So you all must have heard of gravity, right? And gravity, and next word for gravity is acceleration due to right. Acceleration due to free fall. So as the object falls, the apple is experiencing an acceleration, which we know as being gravity. Right? So if you were to take this here and find the gradient, you are going to get something close to 9.8. Right? Which is gravity. So what does that say? Well, what that says is that acceleration, yeah. See right now here? Yeah, something just went wrong. Sarah? Anybody here? No? All right, yeah, something that's freeze there. Anybody here now? You all here now? But I said, oh. Online? You all here now? You all here for one simulation? No, I wasn't seeing anything as well. Oh, you're over here? Oh, shucks. All right, well, I'll delete it anyway. I'm going to it back here. So here's what we're looking at. We're looking at that new quantity called acceleration. And acceleration happens when there is a change in velocity. Right? So as the apple was falling, there was an acceleration because the velocity kept changing with time. So acceleration is a change in velocity over time. And the SI unit is meters per second. What would happen, Adrian, if the velocity not changing? Yeah. Huh? No, not changing. Right? So if the velocity is constant, is any change? This implies no change. No change in velocity. And if there's no change in velocity, there is no acceleration. All right? So the term acceleration has to do with change in velocity. If your velocity changing, then there is acceleration. If not, no acceleration. Okay? And let's use the term Adrian was talking about. If the velocity is decreasing, then we have something called deceleration. All right? Oh, my heart looking back. Ready? Let's try a small calculus. All right, so let's take a question here. Can I zoom in better on that way?
Yeah. Yeah.
Right, take a little read there. Let's see if we can answer something like this, right?
Oh, yeah.
Option.
And I feel it.
So in 2008, I read it, and you can draw a small diagram if you want. So you have an idea of what happened in the full 100 meters, right? Right, he completed 100 meters in 9.69. He accelerated uniformly, so that means that his velocity was changing for the first 3.5 before coasting. What does coasting mean? Constant speed, right? So you're moving but at constant speed. That's okay, Lucas? Right? So let's see if you can work that out now. Draw a diagram with all the info and then we start to work it out. Have fun. Try that, man. Draw a diagram first and I'm gonna help you out.
Why is the one that was nice?
Are they get you? Good question, I don't know. All right, so what you should have is a small diagram, right? So he starts here at 100 meters. Oh my God. So draw the line, right? 0 to 100, and somewhere in between put 60 meters. I'll draw it that's now, right? So you starting at 0, then you finish at 100. And then he said that he took, right? That is 0 mark. Then you have your 100-meter mark. Then he said somewhere down the line is 60 meters. He said his total time was 9.69. And he took 6.5 seconds here. So you put in 6.5 seconds here. And you go 60 meters. And then just make a note, here is constant velocity. So from 60 to 100, will he have any acceleration? And Lucas? Any acceleration after 60? No. So his acceleration only happen where? From 0 to 60. Right. Read part 1 and see if you can find the average speed. Look at the formula for speed and tell me how you think we could find speed. Hello? Yeah. Yeah. But I got true? Yeah, so the average speed. So first part is average speed, that is total distance over total time. Over total time. So your average speed so far is that'll be 60 over 6.5. How much is that? Right, so that are important. 9.2 meters per second, right? 9.23 meters per second. No, total distance is 6.5 seconds. Right? Question after is 6.5 seconds. 9 point. You put in the same thing, 60 over 6.5. How much you got? Right. Yeah, 9.2. Two significant figures. Right? Get the habit of using two significant figures. All right, nice. Next part. If you look underneath here, here what they asked for now. What was his maximum speed? So think about the scenario, Benaya. Think about the scenario. And where do you think his maximum speed would have happened? Right? The question, and they said that he maintained or coasted at maximum speed after 60. Right. So now to find the maximum speed, you have to use what happened in here. Okay? No, speed, same formula. Speed is, oh, I don't have to say it. Distance on time. Distance over time. So what would be the distance we covered? 40 and time it up.
419.
Right, 9.69 minus 6.5. That's it. That's when I know spread came all over the place. How much is that?
12.5.
So its maximum speed is 12.5. Online, any questions? Next part. What was the acceleration? Find the acceleration in the first 6.5. How did we find acceleration again? Change in velocity. Right? So I know I didn't give it to you. I didn't tell you what V and U is, but V is your final velocity and U is your initial velocity. So in the first 6.5 seconds, see if you can work out that. What's the acceleration? V is your final velocity and U is your initial velocity. Try that, please. V minus U and T. Right? So what's the initial velocity of both? 0, they start from rest, right? And what's this final velocity by 6.5? Think about that. What's his final velocity at 60 meter mark? Is it 9.23 or 12.52? 9.23 is his average velocity. So if you add up all his speeds and divide it by the total, you get an average. Remember they said when he reaches 60 meter mark, he reaches max velocity. Remember that? At the 60 meter mark, he hit his max speed and then maintained it. So therefore, the final velocity at the 60 meter mark is 12.53. That makes sense, Lucas? Adrian? That makes sense? You sure? So you're using 12.53 and 0. And what's the time you're using, Adrian? 6.5. Okay? Why what? But the question said equals 6. Part 3. Okay? So it's important. I know I find the diagram helps a lot. If you take the info and you write everything down in a diagram, you don't want to keep reading the question over and over. Everything is in a diagram. Right? Work it out and then convert to meters per second, right? Square. Oh, the video on it. Yeah, he said he picks all the videos. That's even know what we do. Anytime something missing, just message me out. Message up. Right, that's part 1, that's part 2 was here. Part 3 now. Acceleration is equal to V minus U1T. Right, so V, that would have been 12.53, U is 0, and T is 6.5. What is that? 1.29.
1.93. Yeah, from
1.93 meters per second squared. For the SI unit, right? Meters per second squared. I think I have one more part. I think I can do that. Next is energy.
Energy. Oh.
No, I'm not doing that. I'll show you that. Finish it? Finish? Put it there. All right. So here's a graph now, right? That's the graph of the journey. I don't want it to draw the graph. I'll zoom in a little bit. Here's what they are. I'll zoom in here, right? Right? What you see? Oh, shucks. I can't see. Hold on, yeah. Online, you all can see the zoomed up image, or you'll see in the entire question. Okay. All right. What is here? Time is in. So this is a graph, right? And the graph gave us velocity on the y and time on the x. I want you to try to figure out, here the question asks us. Question asks, calculate the acceleration of the truck in the first 50 seconds. How are you doing that from a graph? They didn't give you any words or anything. That's all they give you. And they said to find the acceleration, find the acceleration in the first 50 seconds. So try it. Try and see if you can find the acceleration using the graph. Same formula, nothing changes, right? And let's do more questions on this, right? Fine. But it is the wheels. Only 30. Maybe you just early. Area, coming from hospital. Right. Any ideas? Any ideas, Sasha? Nothing else yet? Online? If you get a value, send it. Remember, acceleration is v minus u/t. How much again? 3. Check it back. Close there. 5 or 0? No, it will start at 0. Right? So your final velocity is what? 20. You're saying that? From the graph, you're seeing your final velocity is 20 and your initial velocity is 0. And the time it took would have been 50 seconds. You know, see that? But no, but you're seeing after 50 seconds from the graph, the velocity is 20. And then where did the graph start from? 0. So it means that your initial velocity would have been 0. So it's 20 minus 0 over 50, which is 0.4 meters per second squared. Anybody could tell me technically what you all just found? So somebody just say it. Gradient. Right? So write this down. Note that on a velocity time graph, the gradient gives the acceleration. Okay? Right, last part of it. And I'm helping you. If you get it, don't stop in class if you get this out. Here's what it is. In that 50 seconds, was the total distance traveled? Think about it. What do you think is the distance traveled in that 50 seconds? Try something now. We'll see. Find the distance traveled in the first 50 seconds. Times it. Close. What? Close. I see what you all did. You all had the right logic, but you're missing something. So what you all said is this, right? Look at the diagram. And you're kind of close to it. You all said that speed is equal to distance and time. So therefore, distance is speed by time. You all said that's what you all did, right? Right. That's good. That's good when the speed is the same. But look at the diagram there. The speed changing from 0 to 20. So it varying, it changing. Not staying the same all the time. Huh? So you have to use, so you have to try to use average speed,
And then put it into that.
and then you'll get that. But here's the problem with average speed. It had to get average speed on the graph. Right? So here's what you can do. Let's see if we figure this part out. I'm rubbing this off here, right? So if I were using the part there, if I were using the part here, right? When the speed stay the same, you'll see now there when the graph is horizontal, right? If you had to find the speed when it stayed the same, it was 20 here and it, sorry. Let's pretend this value here is 50, right? You're saying that? And the value here is how much? 20. So therefore, in a case like that, this distance traveled would have been 20 multiplied by 50, which is 100. Right? So this whole thing here is 100 meters. Sorry, not 100. 1,000. So the whole thing there is 1,000. So my challenge to you is how much happens in the first 50 seconds. So your logic was correct for the next 50 seconds because speed was the same. My question is what happens in the first 50 seconds? Watch it again. Here's what I'm saying, right? What I'm trying to say is this. Here would have been 50 and here would have been 20. That's a rectangle length. So when you multiply, you get 1,000 meters. That's this piece here. 500? Watch it good. If you all watch the shape correctly, you all recognize that part having nothing here, right? Because it cut, right? So basically, you just find this area here, which will be half of 50 by 20. So the answer is 500. So because the speed wasn't the same in the first 50 seconds, because the speed wasn't the same, right? They didn't cover as much distance. It was slower than 20. It was around 10, it was around 5, it was around 3. So because of that, it didn't cover the same amount. So in short, to find the distance traveled on a graph, to find the distance traveled, we find the area under the graph. Right? So you find the area under the graph. So the answer is 500. Half of 1,000. All right? Cool. Who said 500? You did? Sorry. Oh, you know, I thought it was wrong because I thought it was 100 and half of 50. Remember I wrote that? I wrote 100? Yeah, I multiplied wrong. Very good, very good, Matthias. Sorry, I had multiplied 50 by 20 and they are 100. Okay, so write this down. Note that the area under a velocity time graph, note that an area under a velocity time graph velocity time graph gives the distance traveled. So you all follow why we have to divide by 2, right? Because the velocity kept changing. If it's constant, then your formula of distance by time will move. Okay? All right. Okay, we'll stop there for today. Right? You have to log out, right? Bye.
No, I thought that was that's not Hey,
Right, so as I was saying, right? So just as a quick review, you should remember that every quadratic looks like this, right? And you should also remember that if it has the roots alpha and theta, then the sum of the roots is minus b on a. Product of the root, we call it product of the roots, c on a. That's okay? And every quadratic can be written how? What was the general form for any quadratic? X squared minus the sum of the roots by x plus the product of the roots. And then you should remember how you find alpha squared plus beta squared. Alpha plus beta all squared minus 2 alpha beta. Right? So there's some small things for you to remember, right? What we're going to do now is the cubic equation version of this, right? God, that's right.
I'll give it out.
Right, so all we're gonna do now is just the same thing. We just adding on the cubic part of it, right?